Hello everyone. In this sessions, today we are going to discuss about application of residue theorem in evaluation of real integrals. So it is come under the topic of contour integration. So what is the difference between the real integrations and contour integrations? So the real integration is evaluated over the real line minus infinity to plus infinity, whereas the contour integration is one of the technique to help us evaluate the complex number. It is evaluated over the contour, which means that the circular one. Okay, in this topic, the application of residue theorem to evaluate real integrals. Okay, before getting to this topic, what is residue theorem? So the residue theorem is nothing but, okay, we have to find out the simple poles and whether it is lies inside the given circle or not, then we have to find out the answers. Okay, now we are going to discuss about the real integrals. So in this sessions, the integral is of the form 0 to 2 pi f of theta d theta. Okay, f of theta, which means that it's a function of theta. It may be sine theta or cos theta. Okay, before getting to the problem, we have to discuss the relation between sine theta and that complex number z. So every one of us know, so z equal to e power I theta, so which is a Euler theorem. So z equal to e power theta, of course we know that e power I theta is cos theta plus I sin theta. So e power theta is cos theta plus I sin theta. Likewise, so 1 by z is e power minus I theta. Okay, then what is e power minus I theta? Which is cos theta minus I sin theta. Okay, so from this, we can correlate the relation. We can find out what is cos theta and sin theta. So how can we find the cos theta? If I'm adding these two, so we can get, so 2 cos theta equal to e power I theta plus e power minus I theta. So cos theta is nothing but e power I theta plus e power minus I theta by 2. Okay, so what is e power I theta? E power I theta is nothing but z. E power minus I theta is 1 by z. So we can replace this. So z plus 1 by z by 2. So what is the relation between that complex number and theta for cos theta? So which is z plus 1 by z by 2. Likewise, we can find out what is sin theta. So instead of adding, if we are subtracting these two, so if I am subtracting these two, what will we get? So 2I sin theta equal to e power I theta minus e power minus I theta. So that sin theta is e power I theta minus e power minus I theta by 2I. So if I am replacing this, sin theta is z by 1 by z by 2I. So in our question, if cos theta is there, we have to replace z plus 1 by z by 2. Sin theta is z minus 1 by z by 2i. Okay, apart from that, we are having d theta. That is differentiations. How can we do that? So z equal to e power I theta. We have to differentiate this with respect to theta. So dz by d theta is equal to I times e power I theta. So because the coefficient of theta is I. So what is the differentiation of e power 2x? So 2 into e power 2x. Likewise, I into e power I theta. So what is e power I theta? Which is nothing but z. So dz equal to I z d theta. From this, what is d theta? We can bring that I z to opposite side. So dz by iz. We have to recollect these three things. Okay, apart from that, the limit. Okay, what is the limit here? This is 0 to 2 pi. So every one of us know. So this is an axis. So this is an 0 degree. That is, there is no angle between this line. So I'm rotating this. I want to get 2 pi degree. So I'm rotating once again. Likewise, so in this one. So you just look at this one. What is this? This is a circle. Okay, circle with any radius. So actually this is a contour one. So for simplicity, we have taken this is a unit circle. So we are considering C is mod Z equal to 1. So these are all the basic things. So before getting to the problem, we have to recollect the fact. Okay, so if it is cos theta, we have to write Z plus 1 by Z by 2. If it is sin theta, Z minus 1 by Z by 2i. Instead of d theta, dz by iz. That circle, that limit is, that contour is mod z equal to 1. Why it's 1? So it's not necessary it is a unit circle. It may be any circle with radius any value, but for simplicity we have taken z equal to 1. Okay. So now we are going to solve the problem by using these concepts. Integral 0 to 2 pi d theta by 13 plus 5 sin theta. So you may ask, is it difficult to solve this problem in real integration? Yes, this problem is not easy to solve by using the direct methodology because the substitution methodology, most of the basic methodology won't work out. So that's why we are using the help of contour integrations. Okay, just we have to recollect the fact. So here sin theta is there. So I am just replacing. So let sin theta is, so z minus 1 by z by 2i. Then d theta is dz by iz. The limit, that is the contour, is mod z equal to 1. Okay, so this fact alone it's enough to recollect. So we can, the remaining and all, it's not necessary to write in the examination point of view, but for your understanding that is important. Okay, now how the given question become? So the given integral I become, so integral over C. So instead of d theta, dz by iz divided by 13 plus 5 times sin theta is z minus 1 by z by 2i. So in the denominator, we have to do the simplifications. So before taking the LCM, here I would like to take that simplification. Just follow here. So dz by iz divided by 13 plus 5 into here z minus 1 by z can be written as z square minus 1 by 2 zi. Just make the difference between 2 and z. So it is easy for the simplifications. Now we have to take the common LCM. So integral over C dz by iz divided by, so the 2 iz is the common LCM. So, okay, so this is 26 zi plus 5 z square minus 5. Okay, so the 2 iz goes to the numerator, reciprocal of the denominator. So this goes to the numerator, or otherwise you can cancel this 2 iz. Okay, this 2 iz goes to the numerator. So this could be written as 2 dz divided by, so here just I would like to rewrite as in the quadratic form. So in the quadratic form, first z square will be coming, then next 26 zi minus 5. Just we are rearranging the denominator term. Zi minus 5. Okay, so this is integral over C. Okay, so now this is now that real integration, that real part of the integration is converted into a complex number. Now the remaining procedure is easy for us by using the residue theorem. What is the residue theorem? So we need to find out the singular points. After that we have to check whether it is lies inside the given circle or not. After that we have to find out the residue. We have to apply the residue formula. then substitute in the final one 2 pi a into sum of the residues. Okay, now we have to find out the singular points. So the singular points are given by, so how will you find the singular points? The singular points are given by denominator is 0. So 5z square plus 26zi minus 5 equal to 0. Okay, so now we have to find out the roots. Okay, as you know that this is a complex number in between, it's difficult to find directly. So what shall we do? So we know that quadratic formula is, every one of us know the quadratic formula. What is the quadratic formula? Minus b plus or minus root of b square minus 4ac by 2a. So by using this formula, we are going to find out the roots. Okay, so here a is 5, b is 26i, c is minus 5. Just we need to replace. So minus 26i plus or minus b square, that is 26i the whole square minus 4 into a is 5, c is minus 5 divided by 2 into 5. So minus 26i, so plus or minus, so what is 26 square? It is 676 I square. So we know that I square value is minus 1. So minus 676. So here 4 5s are 20, 25s are 100, minus into minus become plus. So divided by 10. Okay, so this is minus 26i plus or minus root of minus 576 by 10. So 576 is the square root of 24. Then since negative is inside that square root, it could be calculated as, you know that what is root of minus 1. So root of minus 1 is I. So this is, so minus 26i plus or minus 24i by 10. So the two numbers, what are the two numbers? So this could be written as minus 26i plus 24i divided by 10 and minus 26i minus 24i divided by 10. Okay, so the first one, so minus 26 plus 24, this is minus 2i. So minus 2i by 10 and this is minus 26 minus 24, that is minus 50i by 10. Okay, so I could simplify this, that minus 5. Okay, so the singular points, what are the singular points? The singular points are minus I by 5 comma minus 5i. Okay, so we got the singular points. After find out the singular points, we have to find the nature of the singular points. How can you find the nature of the singular points? So we have to write the factor of the given quadratic term. Okay, so once you are writing the factorized term, it is easy to understand whether it is a simple pole or pole of order something. Based on that only we have to find out the residue theorem. Okay, residue formula. So how can we write? So 5z square plus 26zi minus 5. So how could we write this, the factorize of this one? So 5 into z plus I by 5 into z plus 5i. So some of you having a doubt how we are getting this 5. So hope you can recollect the how we are getting 5 from your school days concept, or otherwise just I am telling you how we are getting this 5. This is the rough work. This is for your understanding only. See, actually these two are the roots. Okay, so if I have to write as a factor form, I have to write only like this. Okay, so actually what is the meaning? If I am multiplying these two, I should get this term because these two are the same. Okay, so shall we try? So just I am doing that multiplication, z square plus 5zi plus iz by 5 plus 5i square by 5. So if I am simplifying this one, what I am getting? So this is 26zi by 5. This is minus 1. So do you think these and these are same? No, right? Okay. So how these two become same? So if I am taking LCM 5 z square plus 26 zi minus 5. So the entirely in the denominator 5 is coming. To, to equalize the 5, so that's why here the 5 is adding. Because, so why you are not getting this 5 here? Since you are making the right answer, you are making the term as 0. So 5x equal to 0, of course x is equal to 0. So in that way only, so since this is not equal to 0, just we are rewriting the given term. So that's why the coefficient of the quadratic term is other than the 1. That term should come in the front. Make a note of it here. Okay. So I am just rubbing the rougher part alone. Okay. Now, so we are rewriting the given term. That is the given integral I equal to 2. We can take it outside since it's a constant. dz by 5 into z plus I by 5 z plus 5y. Okay. Now, so what is the power of this one? Z plus I by 5, the power is 1. Z plus 5y, the power is 1. So both are simple poles. So now we have to write. So minus I by 5 comma minus 5y are simple poles. Okay, next we need to check whether the simple poles lies inside the given circle or not. Okay, tell me what is the given circle? So the given circle C is mod z equal to 1, which means that it is a unit circle. So here just I would like to draw the unit circle, which means that a circle with radius 1 is called unit circle. Okay, so z equal to minus I by 5. So if z equal to minus I by 5, then what is modulus minus I by 5? Which is nothing but modulus 1 by 5. You know that 1 by 5 value is 0.20. So obviously 0.20 is less than 1, which is lies inside the circle. So lies inside the circle, inside the given circle. What is the given circle? The given circle is the unit circle. Okay, we have to check the next point. So what is the next point? So if z equal to minus 5y, okay, then tell me what is that modulus z? Modulus minus 5y, which is nothing but modulus 5. The value of modulus 5 is 5. So obviously which is greater than 1, which means which is lies outside the given circle. Okay. So among the 2 points, one is lies inside the circle. So f of z can be written as so we need to find out a residue for z equal to minus I by 5. Okay. So which is a simple pole. So the residue formula for simple pole. Residue for simple pole. So R of A equal to limit z tends to A, z minus A into f of z. So what is R of minus I by 5? Limit z tends to minus I by 5. So z plus I by 5 into f of z. This is our f of z. So f of z is, so 2 by 5 into z plus I by 5 into z plus 5y. So before substituting the limit, we have to cancel the common terms. So z plus I by 5, z plus I by 5 is getting cancelled. So now, so we have to substitute, we have to substitute z equal to I by 5. Okay, so now, so 2 by 5, so instead of z we are replacing minus I by 5, so minus I by 5 plus 5y. Okay, so now, so 2 by 5, if I am taking I is LCM, so minus I plus 25I. This I and 5 and 5 is getting cancelled. So this is 2 by 24I. So which is nothing but 1 by 12I. So we got the residue answer. So we're having only one simple pole which is lies inside the given circle. So it's not necessary to find residue for 5 minus 5a. The reason is the residue minus 5 is lies outside the given circle. Okay, now at last we come to the end part. Now we are going to find the final answer, which means that we are going to apply the Cauchy residue theorem. So what is Cauchy residue theorem? Residue theorem. So integral over C f of z dz equal to 2 pi a into sum of all residues. Suppose you're having more than a residue point, so you're having more than a singular point which lies inside the circle, you have to find out residue for all such points. So in the problem, we're having only two singular points. Among the two, one lies inside, one lies outside. So it's not an issue. Suppose you're having more than 2 points. So you need to find out, you need to check whether how many points are lie inside. Okay, accordingly, you have to find out that residue. After that, we have to add everything. So here, so 2 pi I into, here we are, since we are having only one residue point, we need to replace it here. So 1 by 12i. So here I am getting cancelled. So we are getting 2 pi by 12, which is pi by 6. So that integral 0 to 2 pi d theta by 13 plus 5 sine theta is pi by 6. Okay, so this is actually a real integral problem, but the real integral problem is evaluated. That is, the real integral problem is converted into a complex number. Okay, so after converted into a complex number, so by applying that Cauchy residue theorem, we got the answer. Okay, so I hope it's clear. So likewise, we are going to solve one more problem. Okay. Okay, you may have a doubt. So if sine theta and cos theta is alone there, we can solve in that, but it's not necessary. Actually, even Palina may also do that. So towards end we will discuss that. Apart from the cos theta and sine theta, if you're having that cos 3 theta or sine 2 theta, whatever may be, okay, in that methodology we are going to see that next problem. So that problem is evaluate 0 to 2 pi cos 3 theta by 5 minus 4 cos theta d theta. Okay, see, the denominator cos theta is known for us. Okay, already we know how to replace that cos theta. We know what is cos theta. So just replacement. Here I can write. So put or let cos, already we discussed, right? Z plus 1 by Z by 2 instead of d theta, that is dz by iz. Then of course the limit 0 to 2 pi, the limit is also, we know that c is mod z equal to 1. Okay, now we are having that one part which is cos 3 theta. So you may have, is cos 3 theta, can we write that whole part 3 or 3 times? No, it's not like that. Cos theta is not equal to 3 cos theta, or cos theta is not equal to cos 3 theta, the whole square. Then what should we do? Okay, see, just come here. um, we know that. What is cos 3 theta? How can we rewrite this one? Okay, so we know that e power I 3 theta. Okay, e power I 3 theta is cos 3 theta plus I sin 3 theta. So what is e power I theta? How can we write e power I theta? See, you know that e power x the whole square, which is nothing but e power 2x. Okay, which is not equivalent to e power x square. E power x the whole square is not that. Actually, so this can be written as e power I theta the whole cube. Both will be the same. So how can we write this one? So e power I theta, which is nothing but z cube equal to cos 3 theta plus I sin 3 theta. Actually, we want only cos 3 theta. In our question, only cos 3 theta. There is no plus I sin 3 theta. Then how can we replace this one? In that z cube, this is the real part, cos 3 theta, plus I into sin 3 theta. So that is the imaginary part. So this is a real part, this is an imaginary part. So in the question, if cos 3 theta is there, how can we rewrite? So cos 3 theta can be rewrite. So real part of z cube. Okay, then sine 3 theta, if sine 3 theta is there, so this is nothing but imaginary part of z cube. So accordingly, if any question is asking, if any of the trigonometric function, okay, so other than sine and cos, even tan, so you can rewrite, okay, so cos 3 theta or cos n theta or sine n theta, so you can use this methodology. So in our problem, cos 3 theta, so which is nothing but real part of z cube. So I'm going to rewrite the given question. So the given question can be written as, so I is, so instead of cos 3 theta, so real part of z cube divided by, so 5 minus 4 into z plus 1 by z by 2 instead of d theta, so dz by iz. Okay, so the real part we have to take outside. Okay, because throughout the problem we have to write that real part. Okay, so how can I write this one? So I've just bring that part outside. Real part of, okay, so z cube dz by iz. Here we can do the simplification. So 5 minus 4. So this here we can take the simplification, that is an LCM. So this could be written as z square plus 1 by 2z. So before taking the common LCM, so it is easy for us to simplify like this. Okay, otherwise towards the end we have to do the simplification. It's better to do the simplification then and there. So real part of z cube dz by iz divided by, so here we can take the common LCM, or one time I will write it again. So z square plus 1 by z. Okay, so now we have to take the common LCM. So real part of, this is, here we can cancel one part of z. So z square dz by I. So if I am taking z LCM, so 5z minus 2z square minus 2 divided by z. Okay, so where the z will go? It goes to the numerator. Okay, reciprocal of the denominator, it goes to the numerator. So real part of z cube dz by, of course, everywhere we have to write that integral over c. I missed that. What is c? C is a unit circle. Okay, so by, so 5z minus 2z square minus z. Actually, just look at here. Here, for our convenience, I'm going to rewrite the term. Okay, because always first term will be the quadratic term. So that is easy for us to do the further calculations. Here, minus 2. So what I am doing? So I'm taking minus outside. So if I'm taking minus outside, that is that. Okay, so a real part of minus 1 by I. So this minus is from here, this I is from here. Okay, this is the numerator denominator. So I could write, because this term is a constant, it's unnecessary to keep inside that integration. So z cube dz divided by 2z square minus 5z plus 2, sorry, plus 2. Okay, so here I am pulling minus outside. So this 5 become minus 5, this minus become plus, this minus become plus. I hope it's clear. Okay, now we just leave this part. Consider this part, that is, now what is the next step? We need to find out the singular points. Okay, so we need to find out the singular points. How can we find the singular points? So making the denominator to 0. Okay, so singular points are given by 2z square minus 5z plus 2 equal to 0. Okay, here it's not necessary use the quadratic formula. Of course, you can use the quadratic formula, or otherwise it is easy to split the middle term. And so in school you have studied how can we find the roots for the quadratic equations, either separating the middle term, so or sum and product method, or otherwise that quadratic formula. There are many methodology. So here just I would like to split the middle term, because in the first problem we use the quadratic formula. So here I would like to use the splitting the middle term. Okay, because the previous problem it was difficult to split the middle term, but here it's comparatively easy. Okay, just look at this one. Sum, the sum is minus 5, the product is 2 2s are 4. Okay, the sum is minus 5, the product is minus 4. So what are the two number? Sum is minus 5, the product is 4. The numbers are minus 4 and minus 1. Okay, so I can write 2z square minus 4z minus 4 plus 2 equal to 0. So in the first 2z is common. If I am taking 2z commonly outside, z minus 2. Likewise, from the next term, if I am pulling minus 1 outside, I am getting z minus 2 equal to 0. So here, so z minus 2 is common. The remaining is 2z minus 1 equal to 0. So z equal to 2 and z equal to half. So what are all the singular points? The singular points are z equal to 2 and half, 1 by 2. Okay, so now we need to find the nature of these singular points. So how can we find the nature of the singular points? Next, we have to factorize the denominator. So if you are doing the factorizations, it's easy to understand that power of the term, okay, power of the each term, so that we can understand whether it is a simple pole or it is a pole of higher order. Okay, so considering the denominator. So let 2z square minus 5z plus 2. Okay, so 2z square minus 5z plus 2. So already I told you, since that first term is more than, I mean it's not other than that 1, so that term is multiplied by the first. So z minus 2 into z minus half. Okay, now replace in this given I. So I equal to real part of minus 1 by I integral over C z cube dz by, so 2 into z minus 2 into z minus half. Okay, because see, z minus 2 the whole part, this is 1, of course this is also 1. Okay, so these two singular points are simple pole. Okay, so now we have to write the nature. So z equal to 2 and 1 by 2 are simple poles. Okay, so after identifying the nature, we need to check whether these simple poles or these singular points lies inside the given circle or not. Okay, now again we come to this what is that region? So our region is modulus z equal to 1, which means that it is a unit circle. Okay. So let us consider. So if z equal to 2, so if z equal to 1, so that is modulus 2. So we know that modulus 2 value is 2, so which is greater than 1, which means that which lies outside the given circle, outside the given unit circle. Okay. Next, if z equal to half, so modulus 1 by 2, so which is 1 less than 1. So half is 0.5, which is less than 1. So which means that, so this point, which point? Z equal to 2 lies inside the circle. Sorry. Inside the circle. So we should consider only z equal to half point. So after identifying that location, whether it is lies inside or outside, what should we do? We have to find out the residue for that particular point. Okay. So before that, just I am writing what is f of z, then residue formula. So what is f of z here? So we can write that fully everything. So z cube by 2 into z minus 2 into z minus half. Now residue for z equal to half. Okay, again it is a simple pole. So what is the simple pole formula? R of A equal to limit z tends to A, z minus A into f of z. So limit z tends to half, z minus half into, so this is our f of z. Actually, you can retain this 2 over here also. Okay, because already we having constant part outside. Either you can retain over there or you can bring it here. It's not an issue, but don't miss that. Okay, so at last I should consider this minus 1 by 2a. If you're missing the part, the answer will be wrong. Okay, so make it clear, or otherwise you can keep this 2 also over there. Okay, whatever maybe, we should not miss that. So z minus half is getting cancelled. Now we have to simplify. So 1 by 2 the whole cube divided by 2 into, so 1 by 2 minus 2. Okay, so what is this? This is 1 by 8 divided by 2 into, so this is minus 3 by 2. So this 2 is getting cancelled. I am getting minus 1 by 24. Okay, so this 8 comes to the down, so 8 3s are 24. Okay, now after finding the residue value, we should apply the Cauchy residue theorem. Okay, so by Cauchy residue theorem, so what is Cauchy residue theorem? Integral over C f of z dz equal to 2 pi a into sum of the residues, sum of all residues. So 2 pi a into, see, don't miss this part, okay, minus 1 by I into minus 1 by 24i. Okay, see, because this part evaluation is minus 1 by 24, not I, sorry, my 1 by 24. So actually I missed this minus 1 by I, that is, I have to take this minus 1 by I. So I am considering this minus 1 by I. So this is the formula, 2 pi a into sum of all residues. Now do the simplification, this I and I getting cancelled, minus and by become. So 2 pi by 24 or pi by 12. So we are having one more thing, real part of. Okay, so real part of pi by 12. See, in the pi by 12, everything is a real part. So this is pi by 12 only. So pi by 12 itself a real part. So we are considering this is the answer. So pi by 12 is the answer. Okay, so this is pi by 12. Okay, va? Okay, you may have a doubt. So ma'am, only we having that trigonometric term only should be converted into a complex. No, actually it's not necessary. That polynomial also we can consider. We can convert. Quickly we will go through one problem in this concept. Then wind up. That indefinite integral, that is the limit is minus infinity to infinity, a polynomial which is f of x by q of x dx. This also we can convert into a complex number. By applying Cauchy residue theorem, we can find the answer for this. Okay, how? See, just the one thing, minus infinity to infinity is the limit. Here there are certain conditions. The condition 1, f of x and q of x must be a polynomial. F of x and q of x must be a polynomials in x, of course. The second condition, the degree of q of x, that is the denominator degree greater than the numerator degree at least by 2. Okay, the denominator degree at least 2 greater than the numerator degree. Okay, so greater 2 more than degree of p of x. That one more condition, the denominator should not vanish in any of the real x, which means that the denominator should not have any real numbers, okay, real roots. It should not have the real roots. It should have the imaginary roots. Okay, so q of x does not vanish in any real x. Okay, if it satisfies, we can convert. Okay, what about the limit here? Actually, the limit minus infinity to infinity. Actually, this is a number line, right? So, in the number line minus infinity to infinity, so you know that infinity is just a big number. Okay, that's if it's such a big number. So, what we are doing? So, I am considering one such a large number minus r to r. Then I am covering the entire thing by anti-clockwise directions, r to r, r to minus r. Okay, so which means that here we are getting. Can you see a contour here? What is the contour you can see here? Which is the upper semicircle. So here our region of integration is upper semicircle. Okay, that point alone we have to consider. Okay, in this concept we are going to solve a problem. Integral x square by x square plus 1 into x square plus 4 dx minus infinity to infinity. Okay, again this problem is not that much easy to solve in a direct real integrations. Okay, now we have to check whether it satisfies these norms. So both are new polynomials. Yes, of course. Degree, what is the numerator degree? It is 2. What is the denominator degree? This is 2 and this is 2, that is 4. Then so x square plus 1 equal to 0, x square plus 4 equal to 0 means we are getting x equal to plus or minus I and x equal to plus or minus 2i. So it does not vanish in any of the real x. Okay, now how can we solve this one? See, this can be considered as integral over c f of z dz equal to minus r to r f of x dx plus integral over s f of z dz. What is s? S is the upper semicircle. Okay, so this we are the entire that minus infinity to infinity, how we are converting this into a equation. This can be considered like this equation. Okay, now consider. So what I am going to consider? So the given problem can consider as a integral over c z square by z square plus 1 into z square plus 4 dz. Simply we have to rewrite. So x by z. Okay, this is our left hand side. Now we are going to find the answer for left hand side. From this we are going to find the given answer. Okay, now as usual methodology. Okay, first we have to find out the singular points. See, already you know that. How will you find the singular points? The singular points are given by z square plus 1 equal to 0 and z square plus 4 equal to 0. So z equal to plus or minus I, z equal to plus or minus 2i. Okay, so the singular points are 4 points we are having. Okay, so we will rewrite this point. Okay, how can we rewrite? Integral over c z square z plus I into z minus I, z plus 2i into z minus 2i. Okay, so look at this one. Look at all the degree of the terms. So here 1, 1, 1, 1. So which means that so all the singular points are simple poles. So I minus I, 2I minus 2y are simple poles. Now we need to check whether which points are lies inside that circle. Here what we discussed about that circle, here are the region is upper semicircle. So the region is upper semicircle. See, we don't know the radius of this upper semicircle, we just consider the entire positive plane. See, among the 4 points, which points are lies inside that upper semicircle? There are 2 points. What are all the 2 points? So, I comma 2I lie inside the upper semicircle. So, we should consider that point alone. Okay, we should ignore the other point since the other points are lies below that upper semicircle, which is the out of the focus, out of the region of integrations. Okay, so I comma 2i. Now we need to find out the residue for these two. Okay, already we know how to find out the residue for simple poles. Okay, now R of I. So limit z tends to I, z minus into, so this is our f of z. So this is our f of z. So z square by z plus I into z minus I, z plus 2i into z minus 2i. So before substituting z tends to I, the common term is getting cancelled. Now we need to replace I square by 2i, 3i minus I. Okay. Now we have to do the simplification. Now that I square is minus 1. So this is 6i cube. So minus 6i cube. I into I into I. So I cube, this minus. So this I cube can be written as I square into I. So this is, so minus 1 by 6i. Where this I gone? So I cube can be written as I square into I. I square is minus 1. So this is, that part is gone. We need to find out R of 2i. Limit z tends to 2i, z minus 2i, z square by z plus I into z minus I, z plus 2i into z minus 2i. So before substituting z tends to 2i, so the common terms are getting cancelled. So this is 2i the whole square by 3i, I, 4i. Okay, now we have to do the simplification. This is minus 4, this is 12i cube. So what is 12i cube? 12i cube is nothing but minus 12i. So that minus is getting cancelled. So 1 by 3i. Okay, so that this is on R of I, this is R of 2i. Okay, so already we discussed. So after finding this residue for simple poles, now we need to apply the Cauchy residue theorem. Okay, so I'm rubbing here. So by Cauchy residue theorem, so what is Cauchy residue theorem? Integral over C f of z dz equal to 2 pi a into sum of all residues. So 2 pi I into minus 1 by 6i plus 1 by 3i. Okay, so here we need to take the simplification taking LCM. So 6i is the LCM. So minus 1 plus 2. So this is 2 pi I by 6i. So this is pi by 3. So actually the pi by 3 is the LHS answer. Okay, we need to feed in the LHS part. So 2 minutes, sir. Substitute pi by 3 in equation 1. So pi by 3 equal to minus r to r f of x dx plus integral over s f of z dz. Actually, this part by using Cauchy's lemma. Okay, so by Cauchy's lemma, integral over s f of z dz tends to 0 as z tends to infinity. Okay, so that part is 0. So minus r to r f of x dx equal to pi by 3. Actually, in our question, it is minus infinity to infinity. But here it is minus r to r. So what should we do? Taking r tends to infinity on both sides. So of course there is no r in the right hand side. So the answer become pi by 3. So the what is f of x? The given question is. So this is entirely f of x. The answer is pi by 3. So I hope you understand. So that real integration can be the real integral by using the Cauchy's residue theorem or by converting into a complex number. Easily we can find out the answer. Thank you. I hope it's clear. Thank you. So stop பண்ணிடுறீங்களா?